means, suppose you spin a coin on a smooth table, you spin it. Then you will see that as long as it is spinning, it is either head or tails. See, it can take any course when it falls, isn't it? So that is the superposed state. So that is the analogy we can give. Okay. So this superposition is associated with quantum systems. That means in the microscopic systems. So small objects as nuclei, electrons, elementary particles, photons. So they can exist. Remember, these microscopic particles, we talked about the wave particle duality. So the very moment we talked of wave particle duality, so wave means they need not be localized, isn't it? Therefore, it can, and their energy in classical, they can have an arbitrary amount of energies, but here they have only seen steps. So that is that quanta. That is why the name quanta has come. So the ball's energy will be quantized, meaning that it can take only certain values. So in macroscopic physics, see, you can see that this is so smooth here in classical physics, whereas in quantum physics, it is like steps. So you are going in a smooth escalator without any steps. And this is like an escalator with steps. So as I was explaining, state means any particular way that system can be described. System means it can be the atom. It can be a single electron. It can be 2 electrons. It can be 100 electrons, or it can be 1 million photons. So that can be a system. So these things, see the electron, how we imagine an atom to be. There is a nucleus and the electron is orbiting round, like the earth orbiting round the sun. With that analogy in your mind, you can think the electron is orbiting the nucleus. But remember, of the wave particle duality, the electron state cannot be, it can be in any one of the states because of wave properties, non-localizations. So that means to say now, this is the superposition. The moment we make a measurement, then it falls into one of the states. Either it will be in the ground state or it can be in any one of the higher energy states. So these things, see the electron can be in the orbits, there will be many orbits. The least energy state is known as the ground state. Then the next higher energy state will be known as the first excited state, so on. See, imagine yourself, you are there. When you are angry, slightly angry, you are in one of your excited state. And when you are very angry, you are in another excited state. Okay? You can come down to the ground state by the emission of that energy. So you can imagine the atom to be like that. Now, superposition, there are mathematical equations are there in quantum mechanics, which describes these things. So they can be expressed in terms of equations, because for your classes, these equations will be beyond your textbooks, even the mathematics that you have studied. Therefore, we are doing it without any mathematics. But remember, these equations, like the Newton's laws, whatever equations you have formed, they can give the information on the probability of an electron, in which state it is, all these things. So this is very important for quantum computers. Remember, this superposition is a very important thing for the working of a quantum computer. So we are looking into the technology. All right. So then, again, see, we will see there is a very famous experiment by the name of Schrodinger's cat. Schrodinger was the one who wrote the wave equation for matter. Okay, so wave equations were written for the sound waves, these type of things. So Schrodinger wrote a equation. So he wrote, so let us see how that, let us play that video. Okay.
Volume is not there. Volume, no.
We cannot hear.
Okay, then in mine it is coming. How to connect the sound? Okay. Probably in the hosts, this one sound has to come, or from this. Okay, anyway, all of you observed the video. So, as long as the cat was in the box, it was in a superposed state. So that means either it was dead or alive. But the moment you open the box, it falls into one of the states. It's dead or alive. But when the box was not opened, it was in both the states. See, that is the crux of superposition, quantum superposition. So once it cannot be observed, the superposition cannot be observed, because the moment you observe, it falls into the classical state. Okay. So this is, but quantum computer can use all these superposed states, all these probable states to work out calculations. So this is a very important thing for superposition. Okay. So now you can see that quantum systems, they are very discrete, and classical systems, they will appear as continuous. So the measurement actually destroys the superposition. So at any given time, a system can be described as being in a particular state. So a tossed coin is either in head state or tail state. An electron orbiting an atom could be in the ground state or an excited state. But superposition means it can be in either when it is in superposed. As long as you are not observing, it is in the superposed state. So it is, the big idea is that a particle in a quantum superposition exists as a combination of different states at the same time. And a measurement destroys the superposition. The moment you make the measurement, it destroys it, because it has to fall into a state. Either if it is a cat, dead or alive, or if it is the coin, it is either the head or the tail. So even in light, suppose you have polarized light, there is a horizontal polarized sheet and there is a vertical polarized sheet, then you can see that as we rotate the Polaroids, the light would be transmitted, partly. So you can say that when they are at an angle, the polarized sheets are at an angle, then it will be a superposed state. Both the horizontal as well as the vertical components are coming. See, since you are not introduced to polarization, I am just giving you this experiment idea. Okay, so these can be looked in many of the sources, which I will share in the groups, so your coordinators can actually tell you about those things in more detail. Okay, so this is, we are just giving you ideas about quantum physics, that it is something different. You have to think in a different way. So now there are, I know just now Ahlu Ali sir was asking me if there were to be a pop-up of these questions, or I had created a link for them in the chat box, it would have been easier for you. So just that superposition states are there, quanta you have heard of. So whether some of these things which you feel they are quantized, so that means are they multiples of some small quantity, or they are continuous? Your ideas, I just want to see. What about electric charge? An electron or the electric current, the motion of charges constitutes electric current. So these charges, are they discrete or are they continuous? The charge on the electron. It is an inherent property of some of the particles, these charges. Like mass and like this, charge is also an inherent property. So do you feel that it exists as some quanta, or you feel it is continuous? I just want to see how you will. Yes, very good. Then what about time?
All coordinators, please take photos of your classes and share in the group. All
Time.
coordinators, please take photos and share in the group.
Yeah,
You
you can
three
share.
have done it, but not others.
Yes.
Please take the photographs
Yes.
and
Yeah.
share in the group.
Correct. Time continuous. And then what about length? Cache. Length is continuous. What about our cache? Just now as I was explaining, I hope that you will get it from students.
All coordinators, please take photographs of your classes and share here.
Yes.
The students sitting looking at the screen at the front or back side, please take photographs and send here, so that it also carry the name of your school.
Okay. Then an ink is created by mixing together 50% red ink and 50% yellow ink. An artist uses it to stamp a picture of a sun. If the ink behaves like a quantum system, remember the key word is quantum system. In a half yellow, half red quantum superposition, what are the different options for which the resulting picture could look like? All red, all yellow, or partly yellow and partly red, or this brown. Remember, it is in quantum superposition. Quantum superposition means how it should be appearing. This I am asking the students. In a coin, both head and tail both the states were there. Superposed means both the states were there. Therefore, how it should be appearing? both colors independently. It should be appearing sometimes as yellow, sometimes as red, isn't it? So that should be, it is correct. So this is the how you should understand the thing. Now, you see, this is a very 2015, this photograph had gone viral. And I don't know, because it is in a online mode, I am unable to ask. I'm just asking the coordinators, how many of the students are feeling that it is in red and white and gold, and how many of the students are feeling that it is in black and blue? Roughly, if you can give. You can ask and you can give. Okay. Then how many of you are feeling that it is white and blue? Sorry, black and blue. Sorry. Yes. So you can already see that you are looking. So that means it has already fallen into one of these states. It is not superposed actually. This is a very famous viral photograph. It is not superposition, because superposed means you should see both the color schemes, but you will see only one color scheme. Some of you will see one color scheme and others will see one color scheme. Therefore, it is not superposed. Okay. So it is a very famous, it is a 2015, very old photograph. Okay. So implications of superposition are that it allows quantum computers to process vast number of possibilities simultaneously, making them more powerful than classical computers, means whatever computers now we are working with. Suppose you are looking at the projection system using your computer, that is a classical computer. And encryption, see, we are all sharing. Suppose I'm sending you a message. So it should only be received by you. So that is, you have observed encryptions. So superposition makes it possible, these encryptions. Okay, so that is where it can be used. And it can, fundamental science, it can test the limits of quantum mechanical principles. So superposition, so that means simultaneously in many states. See, we were showing head and tails, but it can be in many states also. Okay, so this is a cornerstone. It is different from classical things. Okay, so this is what I wanted to make it clear. Then interference is one more thing. So that will be very important. So I will just show you a, see, this is how there is a light source. It goes through a slit. Imagine it as a, now light is going like a wave. Okay? And then the waves are spreading like your water waves, which spread. So you can imagine in a similar way, light waves are also spreading in 3 dimensions. So even in, if you imagine it in 2 dimensions, it is fine. Then what is that we observe on the screen? So we observe that there are bright and dark positions. See, if we had thought light as a particle, then we would have observed a bright spot at one, corresponding to one slit, and another bright spot corresponding to other slit. But instead, we are observing bright and dark positions. So this is a purely a wave phenomena, and this is known as light interference. Okay. But suppose we take an electron. See, already we have talked about the dual nature of matter also. Suppose you keep electron only as a particle. Then you send it through the 2 slits. This is an electron gun, shoots electrons. then either it has to go through this slit or go through this slit. So we should be able to see only light at a position corresponding to this above slit or the below slit. But instead, even for the electron, we observe that there are bright and dark regions showing the wave nature of matter also. So this is the interference. So two which are, see, they are derived from the same source. So they have a very constant phase difference. Constant phase difference means when this is one light through one source is attaining maxima, the light through the other slit also may be attaining maxima, or there might be a time lag, but it is maintained. Suppose this is attaining maximum intensity at one time. This may be attaining after a microsecond. So every time this is attaining, this will attain after a microsecond. So that is a constant phase difference is maintained. This is known as coherence. And if they are coherent, then we will observe interference. They will either destroy each other or they will add. So this is interference. Similarly, in electrons also, we have observed these things showing. So this is the interference. Again, one more diagram. See how the light will spread. See, all of you have played with hose. You take water in a hose. So how light will spread? See, in these previous slides, you have observed how it is spreading, So that is, suppose you close the hose with your thumb, then you will observe that the water will spray out. So this is an analogy you can keep in your mind, how light will spread when coming out of those slits. All right. So how it can spread and how interference can happen. Okay. So even with photons, even if you treat light as a stream of particles also, you would be able to see an interference pattern on the slit. But remember, superposition these things. Suppose you were to check through which slit the electron is going, then that moment the interference will be destroyed. So observation destroys these things. See, only now one slit, you will see the intensity like this. And through the other slit, you will see. When both the slits are open, so we expect the electron to show this kind of behavior. But instead, it shows this kind of behavior. But if you want to observe, hey, I want to see, I will send only one electron at a time or two electrons at a time. And I will check through which slit it has passed. I want to see whether electron is behaving like a particle or a wave. The moment how you will see things, you have to send photons, isn't it? Because the photons will scatter light to your eyes and you would be able to see. But the moment you do that, then you will see that there is no interference pattern. So the measurement destroys this behavior. So as long as you are not observing through which slit the electron is going, you will see the interference pattern on the screen. But the moment you try to see through which slit it is going, you will see only the particle behavior. Okay. So both the behaviors are seen. So this is the thing. 1 second. Let me see if I would be able to see any one. Okay. The double slit experiment, I would be able to show it to you.
S1 and S2.
So, this interference also connected closely with superposition will, very useful for the, uh, the quantum technologies. So, then quantum measurements are there, how it can be measured, these quantum systems, because they are now different, because you have to measure probabilities. Therefore, suppose you in classical physics, you want to measure velocity, let us say, then what you will do is you will measure the position of the particle at every time, and then you will find the displacement, then you will divide it by the time. So, it's all taking place in a very easy way. But and the mathematics is also not that difficult. See, it's quite difficult even in classical mechanics. When we go for some more measurements, 2 dimensions, 3 dimensions, the mathematics can get tricky. But in quantum physics, the state of the system, so let us say its position, etc., has now become probably, see, if it is like, it can be like this, it can be like that. So, how much percentage it can be like this, how much percentage it can be like that. Therefore, the mathematics can be a little bit tricky, but very nice. Very nice. Once you understand the nuances, that means the various things associated, you would be able to measure. Okay, so this is the mathematics and all. So how once it collapses and all these things can be done. Then there is what is known as the quantum tunneling. So these are all the effects. This is very useful in data storage and all those things. This quantum tunneling, because they are little higher order concepts. So, and then entanglement is there. So I'm sure that because it would take about another half an hour or so, I'm thinking that I will stop at this stage, and if you have any questions, let us now throw it open for the students.
Yeah, good. I request the coordinators to encourage questions. Students should ask questions. Krishna says in the Bhagavad Gita that pariprashna is important. Keep on asking, pariprashnena sevaya. he says? He says it because the student is the one who considers, thinks, takes on the bladder of your mind and asks questions.
Or if they have not understood some things, they can always come with those things.
Everything you may not understand immediately in the first chance. It
And
takes time to understand. So please ask questions. Do not be shy. Speak,
coordinators
you
can
can write on
convey.
a piece of paper and give it to the coordinator. You can give it to the coordinator on a piece of paper and he or she can ask questions on their behalf also, mentioning their name. We want questions.
Or even your comments, even that is fine. Even you can make comments, and no question is wrong here, because you have been newly introduced to these things.
Coordinators can also ask questions if they have any regarding clarifications or whatever, comments, clarifications. We want every coordinator to convert himself or herself into a speaker. You will be needed to speak to the group like this, like Dr. R.S. Gita did. So, good. What is black body radiation? Good. Name of the student? Okay.
All right, very good. Actually, black body means a hot object. Okay, so enclosed hot object. See, our sun is a black body. It can be approximated to a black body, and it would be giving out light in all possible frequencies, many possible, if not all possible, also many possible frequencies. So the light that is coming out of these hot objects, see, for your thing, I'm just telling it as hot, very hot objects, okay, which are insulated, and then they are giving out the light. So actually we use the word radiations there, but maybe you are not introduced to the word radiations, therefore I'm using light in a general sense of the term. So what frequencies it is giving, so that we study. So that would be the black body radiation, very hot objects. And not you can ask, is earth a black body? It's a very poor approximation for a black body. Earth's normal temperature, its general temperature would be around, anything that has temperature will give out light above 0 degree Kelvin. 0 Kelvin, anything above that will give out light. Okay, so very hot objects will give out. So that you can think of as the black body radiation.
There was a question on interference from South Point School. I want to say that interference simply means mixing. Going back to algebra, we say that a plus b square is a square plus b square plus 2ab, right, in algebra. So the a square and b square are square terms which are independent of the other, that is b or a, whereas ab, that is 2ab, is called as an interference term, because in the interference term both the objects exist, the a and the b, a and the b. That is called interference. Now here we are talking about the waves. Now if there are wave has a characteristic of what we call as a phase. So in that phase, what happens is, if I have two waves with different phases, when they mix, what we get is an interference, like in the case of A into B. right? That is the simple answer. We will elaborate. Photoelectric. You will answer, Gita ma'am?
Yeah.
Yeah.
What is photoelectric effect? Is that the question? What is the question?
What is photoelectric effect?
Okay, that is the question. Okay. Photoelectric means there are some metals, for your think metals would be sufficient. See, metals have a large number of, free electrons in them. So when light of some frequency, some higher frequency, see, radio frequencies are also light waves, but they are of low frequency. Then microwaves are also light waves. They are of lower frequency. Visible light is what, in generally we feel it is light. So that is of comparatively high frequency. Then we have ultraviolet. So that is also light wave, but of very high frequency. Then X-rays are there. They are also light waves of very, very high frequency. Then gamma rays are there. They are also light of very, 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 very high frequency.
Okay, there is a
So
question saying, what is the major difference between wave and a particle? First of all, wave and a particle both are characteristics of materials. And get the word matter, then it will be clear. Matter also involves energy in some way or the other. Wave and the particle. When you consider a large number of particles together, they acquire the properties of a wave. When you consider a large number of of particles together, they slowly acquire a property of wave, something like that. Something like if there are 50, 40 or 50 members of your family together, you have some characteristic of a wave. Similarly, if you are alone or one or only two, then you may not have the property, you may not observe the properties of a wave. If you are family of 50, the wave properties will come out from the system. Whereas if you are one or two, the wave property will not come out of the system. Both wave and particle are such that they transmit energy. They take energy from one place to the other. The difference is in the case of waves, the particles of the medium move only locally, whereas in the case of a particle being thrown, there is no thing like wave, but the entire piece of matter moves from one place to the other. So one carries the momentum called P mass into velocity, whereas the other tends to carry a different kind of a momentum, which we define as E divided by H. For that, you will have to learn a little more differently later. But understand that particles are wave and waves are different in one sense, but they are same in another sense. Thank you. Is photon a particle or wave? Answer is photon can be a
I will say,
particle,
sir.
photon can
Yes,
be a wave, both.
yes. Then
Photon can be a particle, photon can be a wave, both.
Superposition is used. How is it useful for quantum computing? I have told you that it can exist in many states. Therefore, each can be a path for computation. So that way, here there will be only a single path in classical computers. But whereas in classical computers, you have many paths for calculations. So that way, it can do phenomenal number of calculations. So it will be very useful. See, well, wave means non-localized, particle means localized, and a matter as well as photon both can be localized. Too much localized means it will appear as a particle, and non-localized means it will appear as a wave. So this is what is localized means not confined to a single point. So that is the meaning.
There is a question on uncertainty principle. What is uncertainty principle? Uncertainty principle talks about the fact that if you have two observing variables like position and momentum, or energy and time, or angular momentum and this one position, it so happens that both of them cannot be measured accurately. If you want to measure the accuracy of one, say momentum, then you must forget the accuracy of the other, the position. If you want the position to be exactly measured, then the momentum cannot be exactly measured. And that limit is given by the fact that measurement error in position and measurement error in momentum, when multiplied, gives you a limit of h cross h is the small Planck's constant. It is called as a Planck's constant. So understand that both the things, that is energy and time, or momentum and position,
Position.
cannot be measured exactly at the same time. It does not mean that either of them cannot be measured. All that it means that they are paired up in such a way that measurement in one takes away the accuracy of measurement in one, steals away the accuracy of the measurement in the other. That is the whole issue here.
What
The
is
next
Planck's
thing is, what is
postulate
Planck's
means
postulate? Will you
energy
you explain, Geeta ma'am, Planck's postulate?
energy of a photon is given as a constant h, that is known as Planck's constant, multiplied by the frequency of light. So the energy can go as h times frequency, 2 times h frequency, 3 times h frequency. So like this. So that means it will go as steps. So imagine that while climbing, you are going in steps, not smoothly like in a hill. Suppose you don't use the steps at all. So that is non-quantization, but this is quantization. So it will go in some packets, multiplications of some quantums. So that is Planck's postulate. E is equal to n times h. H is a constant, so multiplied by the frequency of light. So I think we have also, it's already 2, and I'm sure all of you. And if you have any questions, please through your coordinators, you can give it to them. They will pass it on, and how best it can be made interactive and we can discuss with you. We will do that. I am highly thankful to Professor Arvind Kulkarni sir for giving this opportunity. And I'm highly thankful to all these schools, who made all the students to come. See, Subramaniam Chandrasekhar, Nobel laureate, always used to say, it seems, if a person comes to listen to a talk, they're actually doing a favor to the speaker, because the speaker, while speaking, they will understand many things. When I'm speaking, I can understand many of the things where I am not giving the things properly, where I have to improve, these kind of things. So I'm highly thankful to all the students, and a very big round of applause for all the students who have attended. And I'm highly thankful to Professor P.K. Ahluwalia and Professor Rekha Gorpade Madam and the entire team of IAPT for making this possible. Thank you once again. Thank you.
Okay, I am closing the thing now in half a minute with a couplet from the Vedas. It says, Sangachadvam Samvadadvam Samvedam Siddhavatam Deva Bhagam Vasvasate Sangha Sanjananam Upasate, which means that coming together for a common cause or a good cause is extremely important, and it serves the purpose of the society, the humanity, and the individual, all entwined into each other. With this, I thank everybody. The speaker first, who has been teaching physics for 40 years in a college here. I forgot to introduce her systematically, Dr. R.S. Geeta, which I'm doing now, and she has been doing a lot of background work also. I also thank Professor Ahluwalia for his comments, Professor Balakrishnan, Professor Sudhakar, and all the people and the school that have joined here. I would request the coordinators to kindly share the photographs of their schools students sitting. Two, three schools have sent, but not all. And with that, we will close. Tomorrow, we will meet at the same time at 12:00. Thank you very much. Tomorrow noon we'll meet. Thank you.